Video, I'll be talking about how to do data analysis with what are called error plots. For this video, as in previous videos, I'll be using data collected by Francis Dalton on the variation in human heights between different families. So the question we'll be addressing in this video is how do we summarize differences between groups? We can use box plots and histograms to investigate the amount of variability in a group, but often we want to boil down the data to some sort of measure of what's the typical value. Usually it's the mean, and we want to often are interested in is the mean of one group different from the mean of another group. So in this example, I've taken Galton's data, and as in a previous video on box plots, I've separated the data out by families that had one child, families that had 6 or more children, and I'm investigating whether there are consistent differences between these two groups, these two types of families. So we can use error plots to summarize differences between groups and infer whether these differences are consistent if we were to repeat our experiment, or if they represent some sort of underlying biological reality. When we look at an error plot, the x-axis are discrete groups. In this case, it's 2 different types of families, 1 child or 6 children, 6 or more children. The y-axis is a numeric variable, some sort of variable measured with precision using an instrument, in this case, Galton's rulers. The mean of these plots, the mean is almost always what is shown in these plots, not the median. If the median is shown on a plot like this, then there better be a note big and easy to see that it's not the mean, it's something else. Usually it's the mean value of the group, so the mean of the families, the height of children that are in families of more than 6 children, 6 or more children. That's represented by some sort of symbol, usually a circle or a square or a dot. You'll sometimes see people, or you'll rather frequently see people represent this type of data using a bar plot. Those are falling out of fashion for a number of reasons, and it's better to use error plots like this. So the mean is represented by a symbol. The symbol extending above and below it are error bars of some kinds. Now, there's lots of different things that error bars can represent. They can be the standard deviation, what's something called the standard error that we'll talk about more in a second, or my preference for most applications, a 95% confidence interval. It's always important anytime a plot is made for whoever made it to indicate exactly what the error bars represent so that the reader knows what they mean. So for the rest of this lesson, I'll be talking about 95% confidence intervals. So the 95% confidence interval refers to the distance from the top of the bar to the bottom of the bar. And each confidence interval is separated out into an upper arm and a lower arm. And it's important to know whether we're talking about the whole confidence interval or the arms. We do our calculations, we calculate the size of the arms, but we often talk about the entire 95% confidence interval from the top arm to the bottom arm. The arms are usually symmetrical in most applications that you run into in intro bio classes and basic biology labs, but it's important to keep an eye out for error bars and 95% confidence intervals that aren't symmetrical. But when they are symmetrical, you calculate the length of one of the arms, and then you use that value for both the upper arm and the lower arm. So again, usually the upper arm and the lower arm are equal length. In more advanced settings, you'll get to situations where they're different. For our purposes, for calculating 95% confidence intervals, we're going to calculate the length of the arm of each arm as 2 times the standard error. Actually, it's closer to 1.96, or it'll vary depending on your exact sample size and what you're doing, but 2 is close enough most of the time when we're doing biology. So the length of this upper arm from the mean to the upper arm is 2 times the standard error, and the length from the mean to the lower bar is 2 times the standard error. So this point here, represented by the top of the bar, is the mean plus 2 times the standard error, and this point here is the mean minus 2 times the standard error. Standard error, we don't always deal with it in intro biology labs and classes, but 95% confidence intervals are really important to understand, so we need to know what a standard error is. It's not too hard to calculate. You just calculate your standard deviation on a calculator or a spreadsheet or by hand, and then divide it by the square root of the sample size. It should say square root here. So standard error equals the standard deviation divided by the square root of the sample size. Sometimes you'll see it written out as SQRT. When you're using a computer, a spreadsheet, or whatnot, that's often how it's written. It's also easier when you're making slides. Those of you who are taking class, you should prepare to stop the video in order to answer the following question proposed to us by Darwin, which is, if the standard error is 2 and the sample size was 10, what is the original standard deviation? This is actually a calculation I end up doing fairly often. You don't always have the information you want, so you take the information you're given, calculate what you need. I often need to know the standard deviation of data for my work, so I take standard error and the sample size and work backwards. So go ahead, if you're taking this class, pause the video and do this calculation, enter it into the course software, and then resume. It's important to emphasize that the precise interpretation of confidence intervals is tricky. Most people who take a basic statistics class still, unfortunately, don't grasp what a 95% confidence interval is. I, as somebody who has done statistics teaching and statistics work for many, many years now, I will still bumble on the definition of a confidence interval because they are inherently tricky to define mathematically and to explain. So what I'll present here is a rough interpretation that will give you a pretty good sense without getting bogged down in the mathematical details. Again, can't emphasize this enough. The precise interpretation of a confidence interval is very tricky. But if you can remember this following definition, this shouldn't lead you too far astray. So you can roughly interpret a confidence interval as the range of values likely to contain all the means of repeated versions of the exact same experiment you just did. This is supposed to be the easy, rough definition, but it's still a little tricky, so I'll say that again. The confidence interval from the bottom to the top, you can interpret it as likely to contain all of the means calculated from precise replications of the experiment you did. So what that means is that we would expect that if Galton repeated this exact same experiment with the same sample size and same rules for running the experiment, that the mean of the repeated experiment would be within the confidence interval. It would not be the same as the previous because the data will be different. There'll be variation due to biological and sampling factors, but the mean will be within the confidence interval. If he repeated it a second time, the mean will be within the confidence interval, a third and a fourth time. However, occasionally the mean will fall outside of the confidence interval if the experiment were to be repeated. So the confidence interval, the mean is the middle, and the confidence interval represents likely values for a repeat of the experiment. So that gives you a sense for where nature is going to end up revealing itself to be. However, it's always possible that a value for the mean will fall outside of the confidence interval, and it's even possible that it'll fall far outside of the confidence interval. Data always varies, and especially in biology, things can always end up being different than your first experiment indicates. One thing to keep an eye out for anytime you're looking at data is to see if the error bars exceed biologically impossible values. And in this example, I've actually made up a little bit of data, but we'll say the y-axis here is the circumference of children, and we'll look at the difference between full-term babies and premature babies. This data is, again, just made up, but anytime a child is born, pretty quickly they measure the circumference of the head, and during regular checkups, they monitor growth by looking at the circumference in the head. And so it's possible that if the data, even though you can't have head circumferences in a real baby be 0 or even less, especially less than 0, it's possible that the data could be such that if you calculate a standard deviation or a standard error or our 95% confidence interval, that error bar, it goes below 0. Now, that means that your error bars are indicating that a possible repeat of the experiment could occur below 0. So think about the definition that I just gave you and think about why that error bar is indicating that a repeat of the experiment could possibly yield a value below 0. And of course, a value below 0 for head circumference is impossible. What this means is that somewhere in their math, they made a wrong choice in how to mathematically treat their data. They should have used a technique that would not allow values to be less than 0. How exactly to do that is beyond the scope of a basic biology class. Important thing to note, again, a common source of confusion, is that the whiskers, the bars extending above box plots, are not error bars. These relate to the range of the value, the minimum and the maximum. On an error plot, on a bar plot, they represent some sort of error interval, confidence interval, standard deviation, standard error. So when you're looking at a plot, make sure you know what type of plot and therefore what type of information the error bars are giving you. Looking forward to the next video in this series. When you look at confidence intervals, they can help you infer if the two groups or the however many groups you're looking at, if the groups are likely to be consistently different, if there is likely to be a biological difference between the groups you're investigating. It's important to say that this has to do with inferring whether things are likely to be consistently different or biologically different. Anytime you collect data, anytime you do statistics, you're using models, you're using math to try to understand nature, which can be highly variable, and it's easy for the repeat of an experiment to yield different data. We'll dive more into that, though, in the next video in this series.